In this section, we're going to talk about orthogonal projections. Now, to motivate this section, let's suppose that we have some vector v, some two-dimensional vector v, which means that we can express v in terms of two components. Let's call them v1 and v2. Now, what do these components actually mean? What are they actually telling us? One way to think of these two components is they're telling us how much of vector v is in the direction of the positive x-axis. How much of vector v is pointing in the direction of the standard unit vector I. And v2 is how much of vector v is pointing in the direction of the standard unit vector j down the positive y-axis. So if we graph these, here's the x-axis, here's the y-axis. Remember that I is the unit vector pointing down the positive x-axis, so this would be 1 unit here. And j points 1 unit in the direction of the positive y-axis. It's a unit vector pointing in the direction of the y-axis. So j goes this way. Okay? So if we have vector v, let's say this is vector v here. What we do with vector v is we break it into two separate directions. The direction, how much of v is going in the direction of I, okay? And v is going this far in the direction of I, okay? So we go v1 units in the I direction. That's how far v goes. And then in the j direction, we go v2 units in the direction of vector j. And so instead of thinking about just vector v, what we're really doing is we're breaking vector v up into two directions. How much in the direction of vector I, the standard unit vector pointing in the x-axis direction, and how much of vector v is going in the direction of vector j, the standard unit vector pointing in the direction of the positive y-axis. Now here's the key though. There's nothing mathematically magical or special about vector I and vector j. These two standard unit vectors, they're standard not because they are special mathematically, but because they are convenient to our coordinate system. They make the math a little easier to do, but there's nothing actually special about them. Okay? Sometimes it makes sense to describe a vector, how much of a vector is in the direction of some other vector, some non-standard unit vector. So here we have the amount of vector v in the direction of vector I. We have the portion of vector v in the direction of vector j, how much of that vector v is going straight up and down, how much of it is going left and right. But say we want to know how much of v is going in some other direction. So let me draw a big picture as an example here, because we're going to need to reference it. Okay, so say we have vector v here, and we're interested in how much of vector v is moving in the direction of some other vector. Let's call it vector d. Okay, what is the component? How much of vector v is moving in the direction of vector d? Okay, so if we draw this, it will look, and I'll try to draw this as best I can. Nope. We draw it here down. There we go. There we go, there we go. Okay, and actually I should probably do it in different colors. There we go. Okay, so notice these are meeting at right angles because I want the full maximum amount of vector v going in the direction of vector d. How much is vector v going in the direction of this other vector? So this amount here, this vector here, is called the projection of vector v onto vector d. Okay? And we sometimes use this notation for it. Scroll down a little bit so we can get a little bit clearer of a view. Vector v with two parallel lines as a subscript. And that means the portion of vector v that is parallel to vector d. Okay? And then this part over here, we're going to call v perp. That's the portion of vector v perpendicular or orthogonal to vector d. Okay? The idea here is if you kind of imagine sun shining down on vector d, on vector v, where d is the ground and the sun's right overhead, the projection is going to be the shadow of vector v onto vector d, onto the ground of vector d. So now let's go through the process of actually finding a formula for calculating this projection vector. So a couple observations are going to help us here. First, the projection vector we're looking for, this projection vector right here that we're looking for, it's pointing in the same direction as vector d. So we should be able to scale vector d and by some scalar and get what we want. The other thing that I'm going to note here is we don't really care about the magnitude of vector d. We just care about its direction. The orthogonal projection, we just drop that orthogonal vector down to where vector d is. And wherever we drop it to, that's our orthogonal projection of vector v onto vector d. So in particular, d could be, for example, maybe it's only that long. We get the same thing. Maybe it's only this long. We get the same thing. Okay, maybe it's even longer. We get the same thing. It's just the amount of v going in that direction. All we care about is the direction. Even if we totally flip the direction of vector d, we get the same thing. So we want some scalar, I'll call it k, times the direction of d. Now to focus on the direction, remember we normalize the vector. So I'm going to normalize vector d here by dividing by its norm. So this is a unit vector pointing in the direction of vector d. So this is some scalar, and our main job here is going to be figuring out what this scalar is, times vector d. We give a special name to this scalar. We call it the component of v in the direction of d. The component of v in the direction of d. And this is similar to what we did up here with I and j in our unit vectors. Okay? So for example, the first component of vector v was v1. We called it the first component because we multiply our unit vector I by v1 to get the amount vector v goes in the direction of I. And so v1 is the component. Similarly down here, k is the magic number that we multiply this unit vector by to figure out how far vector v goes in the direction of d. Okay? So let me use this new notation now in our formula. And just to be perfectly clear, the projection of v onto vector d is a vector. But the component of v onto vector d is a scalar. It's how much we scale this unit vector by to get our projection. Okay? So we know how to calculate this. If we know vector d, we know how to normalize our vector. The main trick here is going to be finding the component of v onto vector d. Okay? We could do that with a little bit of trigonometry. So in this diagram, the component of v is, remember it's a scalar, but it's just going to be, use a different color, this length from here to here. Okay, not a vector, it's a length. That is going to be the component of vector v onto vector d. Okay? So the length of that side is the component. Now, using a little trigonometry here, this side here is the adjacent side of this right triangle I've drawn. This side here is the hypotenuse, so I can use cosine of theta and relate the hypotenuse with the adjacent side. So cosine of theta is equal to the length of the adjacent side, which is the component of vector v in the direction of vector d, divided by the length of the hypotenuse vector, which is the norm of v. Notice you need to be very careful when doing trigonometry with these. Notice I'm not dividing by just v. That would be wrong. Okay, dividing by just v is wrong because the trig functions relate the lengths of the sides of the triangle. So I need the length of the adjacent leg divided by the length of the hypotenuse. V is a vector, so I need to find the length of the vector. Same thing here. Okay, I need this side, which is how much I'm going to scale the unit vector d over norm d by to get that length. Okay. So this, the component of v in the direction of d, that's what we really want. So I'm going to multiply both sides by the norm of v to get what we're looking for here. Okay. And now, great, we have a formula for the component of v in the direction of d. It does involve cosine of the angle here. So if we could do something to help us simplify cosine of the angle, that'd be fantastic. If you remember, the dot product gives us some information about the cosine of that angle. So in particular, remember that if I take the dot product of two vectors, and I'm going to use vector d here, because it's pointing the same direction, angle theta is also the angle between vector v and vector d. I get norm of v, norm of d, times the cosine of the angle between v and d. And it's the same theta, right? Since the projection vector and d are pointing the same direction, it's the same angle between vector v and those vectors. So let's isolate cosine of theta by dividing by norm of v and norm of d both sides. Now you got to be careful here. We're new to vectors. Remember, you can't divide by a vector, which is why we're not, right? We're not dividing by a vector here. We're dividing by the norm of a vector. The norm of a vector is just a number representing its length. We could divide by a plain ordinary number. Okay, so cosine of theta, this cosine of theta, is equal to this. And that's going to be much easier to calculate than trying to figure out what the angle between our vectors is. Let's plug this in right there. Okay. And so the component of vector v in the direction of d, we have that norm of v. And then I'm going to plug in cosine of theta. That's the dot product of vector v and vector d over norm of v and norm of d. And just tidy up a little bit. The norm of v in the numerator here cancel with the norm of v in the denominator here. And so the component of v in the direction of d is just the dot product of v and d divided by the norm of d. So what we really wanted to remember was the projection of v onto d. We found the component of v onto d. So now let's just plug that in here. And we get v dot d over norm d times d over norm d. Okay? All right, so I know that was a bit much, but we have derived the formulas for the projection vector of v onto d, the orthogonal projection of v onto d, and as a mini step to that, we've derived the formula for the component of vector v onto d. So let's summarize. And let me emphasize this is a scalar. The scalar component of vector v onto vector d is, and we use the notation, component of vector v onto vector d is v dot d over the norm of vector d. Okay? And the vector projection or orthogonal projection of vector v onto vector d is, so for this, our notation is the projection of vector v onto vector d. And it's important that you keep straight which vector is which. Okay? We're looking at the projection of vector v onto vector d. Generally, this will not be the same as the projection of vector d onto vector v. So you got to get the order right here. Okay? So this is equal to the component of vector v onto vector d. We have a few formulas for this, for the projection, times vector d over norm of d. But we can also write that, plugging in what the component is, v dot d over the norm of v times the norm of vector d times d over norm of d. Okay. I'm sorry, that's not quite right. There's no norm of v down here, right? Just the norm of d. Okay. And we could simplify that by just combining our denominators down here. If we multiply them together, we get the dot product of v and d over the norm of vector d squared times vector d And then one other way you'll frequently see it, remember if we take the norm of a vector squared, it's the same as the dot product of that vector with itself. Okay, so all of these are equivalent ways to calculate the orthogonal projection of vector v onto vector d. And notice in each case, it is a scalar times a vector. It's scalar vector multiplication. This scalar times this vector. This is the scalar times this vector. This is the scalar times this vector. This is the scalar times this vector. Okay, I know when you look at something like this, it looks like there's a lot of vectors there, and there are. But once we're done with the computations, we just have a scalar. The dot product of two vectors gives us a scalar. The dot product of two vectors gives us a scalar. If we take a scalar and divide by a scalar, we get a scalar. So we're taking that scalar and just multiplying by the vector. Okay? Now I want to point out a couple quick things. First, notice, and I think it's easiest to see with this formula here, notice that we don't care about the magnitude or length of d. I've said this before here, but I really want to emphasize it here. We're just saying how much of vector v is in the direction of vector d. How much of vector v is in the direction of vector d, which means we don't care about the length of vector d, we care about its direction. And so in the formula, we can see that because every time we see vector d, we're dividing by the norm of d. And remember, that normalizes the vector. That changes it into a unit vector. And so it focuses on the direction of the vector and strips out the magnitude, strips out the length. Okay, so it's a little harder to see down here, but up here, you can see that that's what's happening. We do not care about the magnitude of vector d, we care about its direction. I want to do one more quick formula for you. Sometimes it's also useful to find that v perp. Okay, if you want to do that, you first find the projection and then just subtract. If you know what the projection vector is, then your v perp, you just want it to end at v, you want it to start at the projection of v onto d. And so if you subtract those, n minus start, you get v perp. So finally, the component, let's go portion. The portion of vector v orthogonal to vector d is, this is our v perp, and we want to end up at v and start at the projection vector, projection of v onto d. And so that's how we can find that v perp, the portion of v orthogonal to vector d.